We have this expensive mic, and then the little clip that holds it onto the belt is like the cheapest thing ever. I could put it in my pocket, but my pockets aren't that well. I could put it in my back pocket. Maybe that'll work. Back pocket. Put it behind me. Okay, we are jumping ahead by a few slides. And then we're going to jump back. I decided I didn't like the order that they were in. I introduced this idea of hybridization by saying if you look at a molecule like CH4, which is tetrahedral, and then you look at the orbitals we have to make those bonds, the shapes don't match up. And so that gives us means we have a need for new orbitals. All right? So we're going to use this idea that we can combine orbitals and get constructive and destructive interference to make new mathematical combinations of the functions to make hybrid orbitals. Okay? So remember these two ideas, that if you have two wave functions that have the same sign, when you combine them, then where they overlap, the orbital gets bigger. And when they have opposite signs, where they overlap, the orbital will get smaller. Okay? So I'm going to start with the simplest kind of hybridization, which is sp hybridization. All right? So what sp hybridization means is I'm going to take the 1s orbital, or sorry, the 2s orbital, because usually we're on energy level 2 if we're talking about carbon or nitrogen or oxygen. So I'm going to take the 2s orbital and then one of the 2p orbitals. Okay? So I'm combining an s orbital and a p orbital. So the S is the circle, the P is the peanut-shaped thing, and I put them on top of each other because they're on the same atom. So I want to ask myself, if I combine those two orbitals as shown in this top picture, what would the result look like? So remember that shading represents whether the wave function has a positive or a negative value. And remember that the p orbital has a line right down the middle that we call a node, which is where it changes from being positive to negative. So my node in the p orbital runs right down the middle. Okay. So above that line, both of my orbitals are unshaded. So they both have the same sign. So when I put them together this way, what's going to happen to the orbital in that region above the dotted line? It's going to get bigger. Below the line, one of them is shaded, one of them is unshaded. What happens when I combine them there, out of phase? It's going to get smaller. So above the line, we have in-phase overlap. Below the line, we have out of phase. And so the result should be an orbital that gets big above the dotted line and then teeny tiny below the dotted line. So one of the rules when we combine orbitals that I mentioned last time, and you know, I think we're just going to accept it as a rule. We don't need to go into the quantum mechanical reasons for it. But one rule is that if we start with two orbitals, we have to make two new orbitals. We can't take two orbitals and make them into just one. So we have to take the two orbitals and make two new orbitals out of them. So when we combine them in the orientation I showed at the top, we're also going to combine them in the orientation I showed at the bottom. So in the bottom, things are reversed. There I have in-phase overlap on the bottom and out-of-phase overlap on the top. So how is the resulting orbital from that second combination going to turn out? It'll be small on the top and big on the bottom. So my second orbital combination is going to look like this. Just a flipped over version. I didn't draw it as fat. Maybe I'll try and make it look the same shape. Now my stylus is giving out. All right. So I took my s orbital and my p orbital and I combined them. And I got two new orbitals that point in opposite directions. What kind of geometry would that be helpful for? Having two orbitals that point in two opposite directions. A linear molecule. If I have a linear molecule, this would be good because now I have one orbital on the left side to make a bond with an atom over there, and one orbital on the right side to make a bond with an atom over there. So these are what we call sp hybrid orbitals, and they are what we're going to use to make linear molecules. So this is the main concept behind hybridization. You can take the atomic orbitals, put them together, and get new orbitals that have different shapes. And those shapes can be more convenient for us to imagine making bonds to atoms. Okay, so if I have a linear molecule, it's convenient for us to imagine that the s and the p orbital combine, make these two sp hybrid orbitals, and then one points at each of the atoms it's bonding to. So to make any linear molecule, the valence electron orbitals of the central atom must become sp hybridized. That means you'll have one pointed to the left and one pointed to the right. All right, and on the next slide, you can see a drawing of what this sort of looks like, although it's really hard to represent on a flat page. There's two leftover p orbitals because we only used one of the p orbitals. So there's two leftover p orbitals that are perpendicular. So in the notes on your page, you can't necessarily see the colors, but the p orbitals are shown in green, and then the two sp hybrid orbitals are shown in blue. I also built a model of this, so I'm going to put on the webcam so that people at home can see them, and then I'll pass the model around. All right, so here's my attempt to show to the webcam my sp hybridized molecule, or sp hybridized atom. The p orbitals I made purple, and the sp orbitals I made pink, although they have blue tape on them. So my sp orbitals I'm holding in my hands, they point to the left and the right, and then there's two leftover p orbitals. One I'm holding in my fingers right now, and now I'll switch, and here's the other p orbital that I'm holding in my fingers now. Okay, I'm going to pass this around to the class now. And if you're watching at home, when you come in, you should check out the models. Okay. So my two leftover p orbitals are just sitting there perpendicular to the sp hybrid orbitals. You might ask, all right, why are we leaving two leftover orbitals? Well, they come into play in a little bit when we start making bonds, because they can make a different kind of bond. All right, so that is still to come. So that's sp hybridization. It's the simplest one to see pictorially. Most chemistry classes will ask you to just memorize this model. And in the end, I'm going to tell you, you are welcome to just memorize a couple of things. I told you up front that I'm only going to ask, I'm going to highlight which slides you actually need to know from this lecture. But I'm not big on just memorizing if you don't have to. So if you can understand what we did here in this picture, then you'll have a much better idea of what we mean when we talk about hybridization. And if you can't, then, you know, at least we've planted a seed, so in a future chemistry class, maybe you will. All right, so if I have sp2 hybridization, there I'd be combining one s orbital and two of the p orbitals. Okay, so if I take one of the s orbitals and two of the p orbitals, I can combine them mathematically in a way that gives me three new orbitals. And we call those three new orbitals sp2 hybrids. It's similar to the last process, but it's a little bit more complicated, because now instead of just combining two orbitals at a time like we did here, we'd be combining three orbitals at a time. I think for fun, I want to show the mathematical derivation of one of these hybrid orbitals. Okay, so these hybrid orbitals point in a flat triangle, essentially. So they're 120 degrees apart. And so I'm going to show on the next blank slide how we would combine the s orbital and these two p orbitals to make, oops, forgot the pen, to make this one here. So my question is, how do I combine these three atomic orbitals to make that hybrid orbital? All right. So I'm combining my s orbital, and I'm combining one of my p orbitals like this, and I'm combining one of my p orbitals like this. And I'm using it to make a hybrid orbital that points down and to the left a little bit. So this is really just a mathematical combination. All I'm doing is taking a little bit of the s and a little bit of each of the p's to make this one. So if you look at that last orbital, I have my unshaded lobe pointed down and to the left, and if I think about this line here, the angle between the orbital and that line, this angle here, is 30 degrees. So if I want my new orbital to be pointed a little bit down and a lot to the left, what that means is I need a little bit of this up and down orbital, and I need a lot of this left and right orbital. So when I combine those three in that way with a little bit of this, a lot of this one, and a little bit of this s orbital, I end up making this resulting orbital. And it turns out a little here means a quarter of this one, I think, a quarter of this one, and half of that one. When you do these actual combinations, the fraction of each orbital that you use has to add up to 1. So I'd take a quarter of the s orbital, a quarter of the p that's going up and down, and then half of the p that's going left and right, and it would result in this other orbital. Now, if you understood what I just said, and you want to for fun, you can think about what the coefficients would be for these other two combinations. And you can also check and keep me honest, because I didn't actually prepare and make sure that those coefficients are right. I just came up with them. Actually, you know what? It doesn't make any sense to not do this. Let's do this. To make the second orbital that's pointed a little bit down and to the right, I still want it to go a little bit down. So I need this up and down orbital with the white pointed down. But then, have I drawn the third orbital correctly? No, why not? Well, I only have half of it left, but there's another reason. I want this orbital, my resulting orbital, to point to the right. The way it is right now, I have my shaded lobe to the right, which is going to be destructive interference, which is going to make it stronger on the smaller on the right. So what I really need to do is change the orientation of that one and make it point this way. So it turns out to make this other one, I use a quarter of this plus a quarter of this plus half of this one. And I make that other sp2 hybrid orbital. Now for my third one, do I need any left and right part? No. I've already used all of the left and right orbital, and I want this orbital to just be going straight up, so I don't use any of that last one. So this last orbital is made just from half of this one and half of that one. Now again, maybe that made some sense. Maybe it didn't. What questions do you have? Oh, good question. Sorry, student question. This is why I have you here, to keep me honest. In this last one, I also drew the up and down orbital wrong because I want it to go up this time. So I need the unshaded lobe to be up. Yeah. So this whole mathematical thing is just taking bits and pieces of the orbitals that we're combining and putting them together in a new way to give us orbitals with shapes that we want. So that's how to do sp2 hybridization. And we do that for anything that's trigonal planar. So I made a couple of models of this one. Well, here's one. I didn't label it with tape this time. Oh, this one's labeled. So here's a model of an sp2 hybridized atom. Okay, it's got the 3 sp2 orbitals around the middle. They're 120 degrees apart. I've shown them in blue here. And then I have the p orbital that's going up and down. I labeled that as pz. Usually the up and down direction is what we call the z-axis. So there's one model. Here's another model in which I've made the sp2 hybrid orbitals pink, and then the p orbital is purple. So I'll pass those around. And definitely check them out when you come to the classroom. All right, so that's 2 of our hybridizations. The last hybridization is sp3 hybridization, so this is where I'm going to backtrack. Our story started with the question of how do we make the bonds in CH4, which is tetrahedral, with these orbitals that are not tetrahedral. So we have the s orbital and the 3p orbitals. They're not tetrahedral in any way. So how do I make CH4? Well, the answer is we make sp3 hybridized orbitals. And in this case, we combine the s orbital with all 3 p orbitals. Now there's going to be no p orbitals left over. Yeah, sorry, we backtracked a little bit, I think, for this slide. We make 4 sp3 hybrid orbitals, and my drawings for these, these are not very good drawings because this is not flat. This is 3-dimensional, so it's hard to draw. But the sp3 hybrid orbitals point in tetrahedral directions. So I've got a model of sp3 hybridization. It basically looks like a CH4 molecule where I've just put orbitals instead of atoms. So here those hybrid orbitals are purple. So this is what an sp3 hybridized atom would look like, more or less. And I'm not going to go through the mathematical part for that because in 3 dimensions it just becomes that much more complicated. The way we imagine this, and this is why this slide is here, but I should get rid of this slide, is we normally think of a carbon atom as having, as being 1s2, 2s2, 2p2. So it's got the 2s orbital with 2 electrons in it, and then you've got the 2p orbitals like this. When we imagine carbon being hybridized, instead we say, no, get rid of those 4 orbitals and just replace them with 4 equivalent orbitals that are sp3 hybrid orbitals and put 1 electron in each. I don't think this slide, I don't think those drawings, though, necessarily are going to elucidate anything for you. But I know people get upset if there's a slide that's not filled in. So what we're doing is we're saying this atom, before making bonds, is saying to itself, let me reorganize my orbitals, put 1 electron in each, and then they're all just ready to go and bond with stuff. I will say this hybridization is a model, and hybridization is not an actual fundamental thing. Atoms don't necessarily say to themselves, oh, it's very inconvenient to have these orbital shapes, so I better change my orbital shapes before I bond. This is something that we impose to make it easier for us to imagine how atoms bond with each other. All right, so now I promised I would highlight when we got to something that you actually need to know. So it's this slide. You actually need to know this slide. You need to be able to associate an electron pair geometry with a hybridization. So for linear, we said the hybridization is sp, and then there's 2 leftover p orbitals. For trigonal planar, the hybridization is sp2, and then there's 1 leftover p orbital. And then for tetrahedral, sp3, and then there's no leftover p orbitals. And those leftover p orbitals become important when we start trying to make bonds. Here's an animation of the orbitals being made.
Hybrid orbitals are formed by a mixing of the hydrogen-like s, p, and d orbitals that characterize a free atom.
And this video always brings up this debate in my head. Machine or person? I can't tell.
The 3 p orbitals are directed along the x, y, and z axes. When we mix an s and a px orbital, we produce 2 hybrid orbitals called sp pointed in opposite directions along the x-axis. Mixing of an s with the px and py orbitals produces 3 equivalent hybrid orbitals in the xy plane. We call these sp2 hybrid orbitals. Notice that the hybrid orbitals have major lobes which contain most of the electron density in the orbital. These are used in bonding to other atoms. Mixing of the s with all 3 p orbitals results in formation of 4 equivalent sp3 hybrid orbitals, directed toward the apices of a tetrahedron. Let's apply the concept of hybridization to ammonia. Here is the Lewis structure for ammonia. There are 4 electron pairs in the nitrogen valence orbitals. We know that an ammonia molecule has a pyramidal shape. This shape can be explained by assuming that the central nitrogen atom employs sp3 hybrid orbitals. The unshared electron pair occupies the 4th sp3 hybrid orbital.
All right, I'm going to show the beginning again just because it was hard to see on screen.
Sp and d orbitals that characterize a free atom. The 3 p orbitals are directed along the x, y, and z axes. When we mix an s and a px orbital, we produce 2 hybrid orbitals called sp pointed in opposite directions along the x-axis. Mixing of an s with the px and py orbitals produces 3 equivalent hybrid orbitals in the xy plane. We call these sp2 hybrid orbitals. Notice that the hybrid orbitals have major lobes which contain most of the electron density in the orbital. These are used in bonding to other atoms. Mixing of the s with all 3 p orbitals results in formation of 4 equivalent sp3 hybrid orbitals, directed toward the apices of a tetrahedron.
All right, so while I was watching that, I realized I made a mistake. here on the coefficients page. And most of you are like, yeah, I didn't pay much attention anyway because I had no idea what you were talking about. But if you were paying attention, I want to make sure I fix this. These should actually be a third, a sixth, so a third, a sixth, and then here this should be 2/3 and 1/3. Not important for you to know these numbers or anything, but the point is each of the sp hybrid orbitals gets a third of its parentage, so to speak, from the s orbital, and then 2/3 from the p orbitals. So, like I said before, I forgot to prepare and actually write down the coefficients ahead of time, but that's what they should be. Question? Well, so the question is about the orientation of the p orbitals, and for px and py and pz, is the orientation always the same way? So the shaded lobe and the unshaded lobe, we want to remember they actually don't mean anything in terms of charge. So they're both representing electron density, so they're both negative. What the shaded and unshaded represent is whether the wave function has a positive or a negative value. Remember, the value of the wave function is not what ends up being important. What ends up being important is the value of the wave function squared. So that's why whether the wave function is positive or negative, when you square it, you always get a positive probability. And so those two lobes in terms of electron density are exactly identical. As far as which direction it has the positive phase and which direction it has the negative phase, that's an arbitrary decision on our part. And like whether shaded is positive and unshaded is negative really doesn't matter. All that matters is when you're combining orbitals, what's the relative phase between the pieces that you're combining. Because if they're both shaded, that's constructive interference. If they're both unshaded, that's constructive interference. But if they have opposite shading, that'll be destructive interference. But when we combine them, we kind of choose what orientation to use. So it's not a fixed thing. So the question is about if you have atoms with more than 4 domains. Right? My slide here that I said you need to know only has 3 of them. And thankfully, the AP people actually got rid of insistence on making you know hybridizations for things with more than 4 domains, because there's a fairly good consensus among chemists that those hybridizations which you may have learned in honors chem, they're not a good model. So you may have talked about sp3d hybridization or dsp3 hybridization before. You can just let that go out of your brain. So don't get the d orbitals involved. And don't worry about hybridization for things that go over an octet. So just these 3 you need to know. And if you understand where they come from a little bit, great. If you don't, you're still going to be okay. So you'll notice on problem set 6, most of problem set 6 is going to be just more drawing Lewis structures and then just adding the layer of assigning hybridization. The next thing we're going to do, which we'll do on Monday, is apply hybridization to actual bonding. And so the other thing that you're going to need to take away from this is the 2 different kinds of bonds that we can make using these orbitals, which are called sigma and pi bonds. So the question is, if you have a molecule that's linear, does that mean those bonds are made from sp hybrid orbitals? And the answer is yes, except with the caveat that this is just one model. So this is one way we can think about the bonding as being from these hybrid orbitals. But like anything else when we're talking about atoms, it's all just a theory. It's all just a model. And there are multiple ways you can actually approach the problem. hybridization is maybe the simplest way to approach the problem of making bonds using orbitals, but there are other models. So I don't want you to think of hybridization as the truth, but as one model that we use. And in the AP curriculum, they actually were explicit in writing the new curriculum saying, you know, hybridization is not something that's an accepted, like, this is how it is. It's more of a model that some scientists don't even feel the need to use. I will tell you, in my organic chemistry classes that I teach, we use the hybridization model a lot because it's relatively simple, and when you're dealing, the bigger the molecule you're dealing with, the more simplifications you want to make to be able to understand it. There are more complicated ways to combine orbitals and make bonds, but sometimes something that's more complicated and more, quote, correct isn't necessarily the best model to use because it might just be too complicated for you to actually make any light out of anything. So the question, next student question is, do we need to be able to figure out these fractions? And the answer is definitively no, no, no. You do not need to be able to do anything that's on any of the slides up to here, up to that one. Okay? Would I like you to have some understanding of those things? Yeah, I'd love it. But most of what I talked about up to this point was so that you could maybe have a groundwork that when you go into a course where you use this theory in more detail, that you'll be in a good place to understand it. But yeah, as far as what you need to be able to do, this slide is it so far. All right, we'll call it a day there.